Thank you for joining the Fire Suppression Systems Association's webinar on Detection Options in ESS and Power Generation Applications. Your phone lines have been muted. If you have any questions during the presentation, please type them in the question box on your webinar control box, and we'll take them at the end of the presentation. This webinar is being recorded and will be available to view after the presentation is over. With us today, we have our webinar chair, Todd Stevens with Canistraro, and our presenter, Ryan Sandler with ADT Commercial. I'll now turn the mic over to Todd to introduce our presenter.
Thank you, Becca, and welcome to everybody that's online. Welcome to all the FSSA members as well as our non-members. We're thrilled that you're here today. I'm thrilled to be here today with our presenter, Ryan. We have a great presentation in front of us, and I'm happy that you could all join. Before we start, I did want to just mention that everybody is familiar with the FSSA annual forum that we hold sometime at the end of February, beginning of March every year. We have made decisions that next 2021 FSSA annual forum will be a virtual forum. We have a lot of really cool things that we're planning for that, and just wanted to give everybody a heads up and let you know to keep your eyes out for emails in the future with more information. With that said, let's jump into the presentation. As Becca mentioned, we're going to be talking about detection options in ESS and power generation applications. Our presenter, Ryan Sandler, is with us today. Ryan has been in the fire life industry since 2004. He's worked for companies like Firelight Alarms as a regional manager. He's been with Siemens as a territory manager, and he's been with Extralis as a director of sales, and currently is the director of industrial affairs for ADT Commercial as a member of the National Fire and Life Safety Team. He's managing the National Fire Design Team and leading the organization's commitment to industry codes and standards. Ryan is also NICET certified, a member of the ICC FCAC working groups, committee principal for NFPA 170, and past alternate for NFPA 101. Really excited about this presentation. Again, thank you for everyone joining, and Ryan, I'm going to hand it over to you.
Thank you, everybody, and good morning and good afternoon. Thank you for joining today's presentation on advanced detection strategies for energy storage systems and power generation. As mentioned, I am a member of the National Fire and Life Safety Team for ADT Commercial, Director of Industry Affairs. And today we're going to talk about energy storage systems. A lot of the references that we're going to use in today's presentation come directly from NFPA 855, the standard for energy storage systems, stationary energy storage systems. So some of the code references that we may touch on, not all of them, but NFPA 1, NFPA 101, 70, 72, 75. We'll even touch on UL 95, 40A as it relates to the certification listings for lithium-ion batteries. For some of you that are new to the industry, or some of the terms that we're going to talk about during today's presentation, energy storage systems, ESS, is the nomenclature that we use for it. Energy storage systems are one or more devices assembled together, capable of storing energy in order to supply electrical energy at a future date and time to local power loads, to utility grids, or for grid support. An energy storage management system is a system that monitors, controls, and optimizes the performance of an energy storage system and has the ability to control the disconnection of the energy storage system itself during any type of abnormal conditions. The battery management system, this is critical to energy storage systems, a system that monitors and controls and optimizes the performance of individual or multiple battery modules in an energy storage system, and also has the ability to disconnect and control the module or modules from the system in the event that it is in an abnormal condition. A cell is the basic electrochemical unit itself, characterized by an anode and an cathode, used to receive, store, and deliver electrical energy. And then finally, one of the most common terms that we're probably going to use during the presentation is off-gassing. Off-gassing is the event in which the cell case vents due to a rise in internal pressure of the cell. And we'll talk about a couple different types of batteries. There's cylindrical type batteries as well as pouch type batteries. And we'll explain the difference between those as we get into the presentation. So if you take a holistic look at the energy storage industry, where it's at today and how quickly it is growing, this graph is a good representation of where we're at and where we're going. You can see there's going to be rapid pace growth in the industry all the way through to 2040. Some of the states that are leading in technology right now are California, New York, Texas, and also a newcomer in Hawaii. But by 2050, there's over 30 states that have committed to be completely independent of fossil fuels. In order to achieve this, the industry will have to move at a much greater clip than it is today. Technology will have to move at a faster pace, which means that the codes and standards and our risk assessments will have to change at a much greater pace as well. And it will require a significant amount of investment in energy storage systems as the industry grows. Taking a little bit of a look at the background behind lithium. Of course, lithium is the third element on the periodic table. As you can appreciate, today, many of electronics and handheld devices are using lithium-ion batteries to power them, such as computers, cell phones, cars, even e-cigarettes. The primary reason for lithium-ion batteries being used in most of our devices is large part because of the advantages that lithium-ion provides. In 1980, a physicist by the name of Professor John Goodenough invented a new type of battery known as the lithium-ion, and what he created was the ability for the ion itself to move from one electrode to another. And we'll dive into what that actually looks like. I have a few slides that talk about the animation inside of the battery and the inner workings inside the battery. But some of the advantages that this type of invention and technology that has given us has, of course, given us faster charging times, longer lasting batteries that can have a greater density to hold charges, and also has a longer lifetime. So we consider lifetime as cycle counts. So if you, for example, if you're charging your phone from 0 to 100%, that would be considered one cycle count. Likewise, if you're charging your battery or your phone from 0 to 50%, that would only be considered 0.5%. So the ability or the technology that it provides for longer charging time and cycle counts is really some of the advantages that the lithium-ion has given us. Also, it is the lightest metal of all the metals in the periodic table. Of course, the lithium-ion battery does have its own limitations, and this is really why the industry, the codes and standards are looking to address some of the risks associated with lithium-ion batteries. So we have codes such as NFPA 855 that give us the ability to address these risks, as well as the ICC International Building Codes and IFC codes that are looking to address this. And we also have performance-based standards like NFPA 75 and 76 that are looking to adopt new language as a result of this type of technology. And of course, we have also listing standards, UL 9540A for lithium-ion batteries, the requirement that all batteries must be listed under. As you look at the battery itself, the batteries are relatively fragile and requires protection of the circuit from any type of damage, any type of overcharging or short circuit. So, for example, if you were to take a cell phone, for example, and I know that you've probably seen some of the videos online where you can take a knife and you can puncture the cell phone, or if you were to snap the cell phone in half, you would have an abuse factor that would lead to immediate thermal runaway, causing the phone to explode and catch fire almost immediately. Recently, I was in an airport where this event actually occurred on an airplane, where a passenger had dropped their phone in the seat back, and when they reclined the seat to try to get the phone, or they're fumbling around trying to retrieve the phone actually snapped inside of the seat and exploded in the actual seat itself. So that thermal runaway event caused the airplane to have to divert and land immediately, causing a significant amount of risk to the passengers on the plane itself. So as you can see, there's an increased need and focus on battery management systems and protecting the operating systems from overcharging and overheating. You've seen this in the industry where, say, hoverboards and electric scooters have been abused by overcharging or overheating, causing many fires or explosions in residential homes, and even in commercial buildings where they've been converted to house some of the scooters. I think down in Austin, they've experienced this where they've had houses that were converted to store, what are they called, the bird scooters that you see scattered around the cities. Well, they've been rounded up and then stored into homes that have been converted for commercial use, and there's a significant amount of risk when you put a large amount of these birds in one place. There's not a battery management system, so in large part they're being charged by just plugging into standard outlets, and they're stringing along extension cords, and they're charging them all from a single source, causing a significant amount of risk and hazard in the areas. The batteries themselves are also temperature sensitive, so they require temperature monitoring and cooling. And the industry itself, the technology is pretty much in its infancy. It's not a mature market, which means that the technology is constantly changing. And that means that the chemicals inside of the batteries are changing, and the metals themselves are changing. So as we look in the battery, take a deeper dive into the battery and what it looks like. Here you have an example of the components and the liquids that you'd find inside. On the following slide, I'll show an animation that depicts how the lithium-ion battery, or the lithium ions, move through the separator from one side to another. But on the negative side, you have the anode, and then on the positive side, you have the cathode. And in between the negative and the positive, you have the separator. So the separator is very thin, and it allows for the movement of lithium-ion liquid or particles to move from either the negative side to the positive side, depending on usage, whether you're charging or discharging the battery. And the liquid inside of the battery is known as an electrolyte. And the electrolyte is relatively unique depending on the battery manufacturer and the metals used inside of the battery itself. So this is a good animation. I found this animation at the U.S. Department of Energy. In this animation, we're showing that lithium ions are swimming in the electrolyte from one side to another. So if you're charging the electrolytes, they flow from the positive side to the negative side, and once they are fully once they are fully charged, and you begin to discharge the battery, or you begin to use the battery, they'll flow from the negative side to the positive side. in the electrolyte liquid. The current technology that is in the market today requires that there be the electrolyte liquid inside of the battery. However, many battery manufacturers in the industry are looking for a more stable solution and a more efficient solution that would hopefully eliminate the electrolyte liquid. So if you look at what causes battery failure, we're going to look at some of the abuse factors that could cause battery failure, but really we're going to focus on two main abuse factors during this presentation, and that is overheating and overcharging. They are the most common and the most preventable abuse factors. Additional abuse factors for battery failure could be external damage to the battery and even direct penetration of the battery. These types of abuses are known as mechanical abuses, and of course, we cannot prevent mechanical abuses. So the problem really relies in once the abuse factor occurs and nothing is done to stop, mitigate, or prevent the abuse factor from continuing. This is when the thermal runaway event begins, and after a single battery has begun thermal runaway, it will propagate to additional batteries in the cell and create complete thermal runaway. And of course, once you achieve complete thermal runaway, the event really cannot be stopped and very difficult to put out the fire. Understanding how a thermal runaway event occurs, really, we talk about two main abuse factors. And then earlier we discussed about the lithium liquid called electrolytes. When there is an abuse factor that occurs, like overcharging or overheating, the electrolyte liquid will begin to change state from a liquid to a gas. So in the case of overcharging, let's say, once a liquid changes state to a gas, it creates pressure inside of the battery that will be required to be vented if you're using a cylindrical type battery. Other type batteries, of course, are pouch type batteries. We'll touch on those a little bit later in the presentation. But for cylindrical type batteries, the internal pressure will begin to push the vent open, and now you will have off-gassing from the battery into the protected space. So the problem here is if you allow the abuse factor to continue, then of course you will continue on into thermal runaway. And as the event continues, of course, more gas buildup will occur and more gas will be vented into the space, allowing for the internal pressure and the separator to break down. So really where you have complete thermal runaway that occurs is once that separator that we talked about right here in the middle, in between separating the anode side and the cathode side, once that separator breaks down is really when the liquids begin to mix and they change state to a gas, and that off gas pressure occurs. And so once that off gas occurs is really the critical time at which we want to achieve some form of early warning detection. This is, you'll see in a few slides, we'll talk about that critical time. The South Koreans kind of coined that term as the golden time, and we'll touch on the golden time more during the presentation. But of course, once you achieve thermal runaway, it cannot be stopped. From an overcharging event, I think it's a little bit of a misnomer that if you achieve overcharging, that you'll also have elevated thermal levels as well. And of course, this is not the case. In many cases, overcharging happens at a relatively low temperature, and we'll touch on that later on in the presentation. But once thermal runaway is achieved, that is a exothermic reaction, and it really cannot be prevented. It will create its own oxygen and its own fuel, and the only way really for it to be put out is for it to burn itself out. So If we look at what allows the electrolytes to become a gas, previously we talked about overcharging. So when overcharging is in the chemical process, the anode has too much current and it is touching the liquid. This allows for the chemical reaction to occur and change state from a liquid to a gas, and that's how it changes state. So as I mentioned, during this change of state, it happens at a relatively low temperature, usually at around, let's say, about 115 degrees Fahrenheit, which is pretty typical operating temperature for these type of batteries. There's not a lot of documentation on the market that shows that at that temperature, thermal runaway can be achieved. So there's good data out there that shows that the battery system can operate in those environments. Now, if we look at the overheating process is very much like boiling water, if you will. Just like when you boil water, it changes state from a liquid to a gas. The same is true with the electrolytes inside of the battery. As they're overheated, whether it be from an abuse factor or whether it be from an external factor, maybe a fire event external to the battery, those liquids will begin to boil and change state from a liquid to a gas. And if you're using a cylindrical type battery, they'll be vented into the space. Battery management systems, we touched on this earlier. The abuse factors should be prevented by the battery management system. Every device today has a battery management system, even when you're using your phones. For example, when you charge your phone at night, you're not necessarily worried about the phone overcharging or overheating. That's primarily because of the BMS system inside. Because once the phone has reached 100%, the BMS system shuts down the charging of the system. Even though your device still says that it's charging, it's plugged in, the BMS has in fact prevented the overcharging of the device to continue, and as a result, preventing thermal runaway. So if you were to apply that type of technology to larger type applications, say like energy storage systems or power generation facilities or systems, the BMS is critical, and it's looking at many different types of variables that lead to a thermal runaway event. So increasingly, the BMS system has a daunting task of identifying possible abuse factors and eliminating those risk factors before they become a thermal event. However, because of the advancements in the technology and the rapid pace at which the industry is evolving, the BMS system needs additional support to help prevent thermal runaway. This type of support, we're looking to pair in conjunction with the battery management system, some type of early warning detection. So whether it be through off-gassing or some other form of different types of detection, we want to be able to bring these technologies together and have them work holistically to mitigate or limit or even prevent the thermal event from occurring. So some of the variables that can be overlooked by the battery management system or difficult to identify are the charging and discharging and the controllers, maybe faulty diagnosis of the battery management system, maybe looking at the parameters of detection. So maybe the battery management system has to review the total voltage, numeric temperature, and current, total current all at the same time. So if maybe there's a malfunction in the battery or the battery management system and it's not able to identify this through balance control and thermal management, it needs additional support mechanisms in place to act as not just a redundancy factor, but also to assist in identifying possible thermal runaway events. These type of events are occurring on a more common basis. Of course, probably the most current and tragic fire that we've experienced in energy storage systems was the APS fire out in Surprise, Arizona. In this particular application, the building was a total loss. First responders and firefighters were on site and fighting the fire for at least maybe 3 hours before the building exploded. And really, this became a critical event when the firefighters looked to breach the building. And we'll talk more about what occurred and how that incident happened. But it really has shined a light on the industry and the risk associated with energy storage systems. Even in South Korea, they've experienced large amounts of fires, well over 20 fires since 2017, where the AHJs and electrical engineers have associated risk or fault to pretty much all stakeholders, battery manufacturers, system integrator companies, and even power conversion systems companies. They've sought as having fault or risk associated with energy storage systems. Even Samsung has experienced problems where they were forced to recall a Galaxy Note 7 in their phones, where they had several incidences, and even Boeing has had several incidences of thermal runaway on their planes. So what leads to battery failure? There really are 4 stages that we have to concentrate on when we consider battery failures. The first stage is the abuse factor, and we talked about overcharging and overheating as the 2 main abuse factors that we're going to concentrate on. So of course, overcharging is an electrical abuse and overheating is a thermal abuse. And then we also mentioned the third type of abuse is a mechanical abuse, which is an external factor that we can't really prevent. So where you have direct penetration or damage, an accident, or some type of malfunction in the manufacturing of the device. As we move to the second stage of battery failure, this is really that, going back to that term, that golden time that the South Koreans had coined. This is where off-gas generation occurs. And really, it gives us the opportunity to provide, as an industry, solutions in off-gas detection. So there's several different type of technologies out there for off-gas monitoring, and it's becoming more widely used and accepted as a standard practice for early warning detection. The third stage is the smoke generation stage. And of course, once you reach this particular stage of smoke generation, catastrophic failure is imminent. In many different types of applications, we've used early warning detection, such as air sampling, smoke detection, say in mission critical type facilities like data centers, telecommunication, in different types of applications. But in particular to lithium ion batteries and energy storage systems, by the time we reach the smoke generation stage, it's too late. Thermal runaway occurs at the same time that smoke generation occurs, and it cannot be prevented. And then, of course, at the fourth stage, you do have a thermal event, you do have a fire event, and propagation has occurred where you're moving from a single cell to multiple batteries or multiple modules inside of the energy storage system. So if we look at how we can possibly prevent this cycle from occurring, or some of the steps or actions we can look to limit or mitigate these types of failures, really it is a team event, if you will. Working in conjunction with the battery management system, we need to implement early warning detection devices for off-gassing and also smoke detection. Now, I mentioned smoke detection is a critical stage at which thermal runaway occurs. But in this particular case, what we're talking about with smoke detection is external factors. So this will allow for stakeholders to shut down equipment, allow it to eliminate the overcharging or overheating abuse factor that is occurring. And then monitoring for external fires with early warning smoke detection, in the space or external to the battery module or the battery management system or the energy storage system. So allowing us that critical time, that golden time, to be able to identify a threat from an external source. That's where early warning smoke detection really does play a critical factor. But they do need to work in conjunction with a battery management system in order to stop the abuse factor from occurring. So as we look at the batteries, we talked a little bit of what it looks, what the components look like inside of the battery itself. We talked about the electrolyte liquids. Not all batteries are made equally. As you can appreciate, it's a very competitive environment. It's rapidly growing with technology changes rapidly occurring. So there is no one set of gases, if you will, to be able to look for or detect. You really you need to be able to take a holistic approach in off-gas monitoring. You can't just look for CO, you can't just look for hydrogen or methane, as you will. And this is really where some of the codes and standards are starting to adopt new strategies at addressing energy storage systems. The chemical cocktail inside of the battery, known as the electrolyte, produces a unique off-gas that's specific to every battery manufacturer. And in some cases, or in many cases, the first sign of off-gassing is through a VOC, a volatile organic compound. So having a gas monitoring system or an off-gassing system that can detect both VOCs and the electrolyte chemical cocktail is critical to be able to detect for off-gas. Also, traditional technology that we have on the market today, such as fixed type sensors, are challenged to detect at the lower level limits, which are required for off-gas monitoring. For example, if you were to use, say, an LEL detector to detect carbon monoxide off-gassing, maybe you were detecting at 25 parts per million in that particular scenario, the off-gas or the LEL detector wouldn't be able to detect at a low enough level to prevent or stop the abuse factor and prevent thermal runaway from occurring. So we need to be able to use a sensor that can detect at the very, very low levels required, the lower limits that are required to look for in the off-gas concentration levels. Also, fixed type sensors are challenged by the environment. Many times the energy storage systems are built in high airflow environments where you're looking at cooling, maybe the racks or modules themselves. So much like when we consider smoke detection in mission critical type facilities, you have the requirements to be able to detect smoke as it moves through the path of airflow. And traditional fixed type sensors are challenged to detect in these types of environments. So being able to detect in high airflow environments, and also the lack of cumulative detection that we see from fixed type sensors creates a challenge for the traditional technology. So no matter the situation, in order to prevent thermal runaway, we need a complementary solution with a battery management system and an active early warning detection system. If you hadn't seen what an off-gas monitor looks like, this is a good illustration. You have a controller here in the top connected to some sensors that are placed out in the field, typically in rack, in the path of airflow, actively looking for those VOCs or off-gas levels. And that's being communicated to the BMS system and or the fire alarm control unit, possibly even being used for suppression release or extinguish release as well. When we look at the codes and standards, they're pretty much in their infancy, but they are developing at a rapid pace. NFPA has a number of committee members that are looking to enhance and continue the work that NFPA 855 has brought forth. And of course, the UL 9540A test standards are the test methods for all lithium-ion batteries. But we're even seeing new code adoptions or new code language being introduced into documents like NFPA 75, even the International Building Code or International Fire Code is looking to adopt new language to look at energy storage systems and the risk associated with that. NFPA 75 has introduced language into the annex looking for that electrolyte detection, off-gassing, so specific types of gases where the off-gas can be detected through early warning detection and then work in conjunction with an approved battery management system. So NFPA 75 has adopted language in the annex that talks specifically about that. And many of the committee members are looking to push that code language throughout the additional codes for the requirement of redundancy of off-gas detection. So if you look at the test standard for UL 9540A for lithium-ion batteries, of course, it's a test method that tests all lithium-ion batteries, and it really is pushing the batteries to their limits to a failure state. So initially it looks at the cell level and using an overheating and overcharging abuse factor reaching at the cell level a failure rate, documents that at the cell level, at the module level, at the rack level, and even at the system level. So it's documenting how the batteries responded to the overheating and overcharging event, and of course the risk associated with that. That test method documents not only how the tests were produced, but it also documents at what time it off-gassed and at what temperature thermal runaway was achieved and at what time thermal runaway was achieved. These documents are available to the engineering community, to the AHJ community, to end users and building owners, insurance companies, for example. So if you were to have an energy storage project in your particular jurisdiction, and let's say hypothetically you were using or looking to use, say, Samsung type batteries or maybe LG Chem type batteries, you can reach out and contact UL as an AHJ or a fire consultant and request these reports that were conducted. These are critical parts of the risk assessment, and they'll even document if and how a off-gas monitor was used or present and what type of results were seen. Traditionally, we see in almost every test an off-gas monitor was present and the data was recorded as to whether the gases were detected prior to thermal runaway. And this will allow for you to confirm that pairing early warning detection of off-gas monitoring with battery management systems can prevent thermal runaway from occurring. So are we there yet today? No, we're not there yet today. I mean, obviously the industry is quickly evolving and there's new technology coming onto the market every day. But many of the insurance companies are now requiring early warning detection of off-gas monitoring. We're even seeing AHJs starting to mandate the use of off-gas monitoring. And we even seen city ordinances like in Florida and in Hawaii where they're mandating the requirement for off-gas monitoring or early warning detection. Developers and life safety system integrators, you're seeing there's a large push for training and education of all stakeholders of the value and importance of detection and early detection, that it provides. And utility companies, power generation type users are starting to demand the use of early warning off-gas monitoring. But the technology is still rapidly evolving for sure, and we need to continue to grow with that risk. So looking at some of the battery failures and the abuse factors, I wanted to show you some tests that were done through third parties. DNV did an extensive amount of testing and documented their tests. So I wanted to share with you some of the testing that they had done. This particular test is showing an overcharge electrical abuse factor, where they overcharged the battery at 50 amps. And the particular pouch or cell type used here was a 63 amp hour. And you can see that in the test itself that traditional types of gas sensors would not be able to detect at the lower levels. So early on in the test, before thermal runaway is achieved, there's very little gases, and they're at relatively low levels to be able to detect. Of course, the carbon monoxide with this particular type of battery was most prevalent. However, methane, ethane, and ethylene were present, but they really didn't spike or peak or off gas into the space until thermal runaway was already achieved. So when using, say, LEL detectors, there's no way that we would have been able to have any type of early warning. Of course, at the upper levels, after thermal runaway had already been achieved, an LEL detector would have possibly detected the event. Continuing the overcharging event, you'll notice that the additional gases were released after the thermal runaway event occurred. So hydrogen chloride, hydrogen fluoride, hydrogen were all released into the space through an off gas after thermal runaway had already occurred. But if you see prior to thermal runaway, this blue line here represents the lower explosive limit. We really wouldn't have been able to given us any type of early warning detection from an LEL state until thermal runaway had been achieved. 855 is looking to address the methane portion of the off-gassing. You can see after thermal runaway occurred, the methane portion did spike. And going back to the APS fire that we talked about, that's really where the first responders and firefighters are at risk, is the large amounts of methane that are being off-gassed. And this is where NFPA 855 has introduced new language to require LEL detectors to notify first responders and identify the risk associated with methane in the protected space. And then, of course, as we continue to look at the overcharging event and the off-gas that was associated with it, had we used an off-gas monitor like DNV used in their particular test, that golden time, that early warning detection, could have provided roughly about 6.5 minutes of early warning detection. So during that time period, that golden time from when off-gas occurs here all the way to thermal runaway, is now where we need to work in conjunction with the battery management system to shut down the overcharging of the batteries and eliminate the abuse factor. This will, in a sense, eliminate or prevent the thermal runaway from occurring. So as I mentioned earlier, during that initial stage, off-gas monitors use volatile or organic compounds in conjunction with other types of electrolyte gas monitoring to be able to provide that critical golden time for detection. In this second test here, we show an overcharging and a mitigation factor. So the battery, you'll see in this particular example here, carbon monoxide, methane, ethane, and ethylene are released in the space through off-gassing. This test represented a overcharging event. So earlier we discussed overcharging where you may not experience a rise in temperature, and that's primarily because overcharging occurs at a relatively low temperature. As you can see here in the graph, traditional type sensors, and we'll show in the next graph the temperature associated with that. The traditional type sensors cannot detect at lower levels of off-gassing, and the battery management system may be challenged to detect a overcharging or overheating event because a lack of thermal temperature increase. So waiting for a ppm type detector may be too late. Say if it were detecting at 25 parts per million, for example. That's primarily because the LEL detectors and the technology that are on the market today have what's known as a deadband factor. Deadband factor is the threshold at which the technologies have the ability to detect. And again, they really don't have the ability to go at that lower level limits that are required for detection. So here you see the overcharging event occurring, and of course it happens at relatively low temperature, roughly about 45 degrees Celsius or 113 degrees Fahrenheit. All the data that is available on the market today shows that there are not very many thermal runaway events or fires associated with batteries operating in this temperature range. So while we have an overcharging event occurring, there is no increase in temperature. So the battery management system, while it's doing all its other tasks, may be challenged to provide indication that an abuse factor is occurring. So this is where an off-gas monitor provides critical time and information to be able to address the situation. Continuing on with the overheating event, this particular test is representative of the UL 9540A that demonstrates the stages of battery failure. Here we're seeing an overcharging of the cell. This purple line represents the overcharging of the cell at 5 degrees Celsius or 41 degrees Fahrenheit over each minute. So we're increasing the temperature 5 degrees every minute per the UL 9540A standards. So as the temperature increases, this is where we're starting to subject the cell to a heat or thermal abuse. And about 25 minutes into the test right here is where the cell begins to off-gas, and the off-gas monitor detects the event. And this is really where we're talking about that golden time factor, the difference between the off-gas being detected and thermal runaway being achieved right here in about 36-37 minutes. So that golden time factor that we talked about earlier, that early warning detection, really for this particular example was about a little over 11 and a half minutes. So the smoke detector provides no early warning in this particular example. So as we mentioned, at stage 3 of battery failure, you have smoke, and that's really where the thermal runaway event occurs. So the smoke detector in this test provided no early warning detection. It was only the off-gas monitor that allowed us that golden time factor. In this test here, I mentioned earlier, we talked about cylindrical type batteries. Here in this particular test, we look at pouch type batteries. So the electrolyte liquid or chemical cocktail is housed inside of the pouch, and in large part the pouch doesn't have the ability to vent like a cylindrical battery does. So we're dependent on the seal of the battery pouch itself or the breakdown of the pouch in order to vent the gas as pressure builds up inside of the pouch. The first graph at the top here is representative of the previous slide, where it shows how the cell is heated at 5 degrees Celsius, and it reaches thermal runaway here at roughly about, again, 37 minutes. And the golden time factor in between that of where the off-gas monitor detected the event. So for this particular test, the golden time was roughly about 6 minutes. In the graph on the bottom, you'll see that that when off gas is detected, we stop or eliminate the abuse factor from occurring, and this prevents thermal runaway from occurring. So here we used a battery management system to stop the overheating of the cell itself, and we prevented thermal runaway from occurring. Going back to the APS fire, we talked in large part about the methane buildup, and really in order for combustion to occur, we need an environment that allows for the right mixture of oxygen and methane to occur. So if the environment's too lean for combustion, combustion can occur, and if it's too rich, combustion can occur. So we need that critical stage for methane and oxygen to create the explosive combustion environment. And that's really what happened at the APS fire, is that the off gas continued and the abuse factors continued throughout thermal runaway, filled the space with methane over a 3-hour period while firefighters were fighting from the exterior. And as they looked to breach the building, they introduced oxygen into the space, creating an explosive environment. So I put together a couple different videos for you to review. This is an example of a cylindrical type battery being overcharged and then off-gassing. So you'll see here at the top of the battery, as we overcharge it, the battery will pop and off-gas right into this space right at the top of the battery here where the shadow is seen. You'll see like a sparkle or a moisture content pop out, and that's really where off-gas is going to be detected. Here, boom, pop of the battery, and off-gas occurs. It happens relatively quick, so I'll play it one more time for you. Again, you're going to look for the battery to pop right here and off-gas right here. Pop, and then it's the off-gas. So as you can see, it's a very quick event. It happens at relatively low levels, and we need to be able to identify that as quick as possible. This particular video shows where an event where smoke has generated. We've gone past the off-gas stage and into the third stage of smoke, and thermal runaway has begun. So I'll play this video. Now, one point that I will point out here is if we're using early warning smoke detection, much like we would see in, say, a data center where you have a cold aisle configuration and a hot aisle configuration, and you have cooling from back of the rack to the front of the rack, we'll want to look for external factors of early warning detection. So fire that's outside of the battery or cells or modules themselves, they could provide an external abuse factor.
지난 7월 한 풍력발전소에서 ESS7을 가득 채운 배터리 부분에서 검은 연기가 피어오르더니 3분 만에 스파크와 함께 불길이 솟구쳤습니다. 배터리 충전 과정에서 전류가 증가하며 열이 나서 배터리 온도가 급상승하는 열폭주 현상이 의심되는 장면입니다. ESS 화재 가운데 4건에 대해 국가수는 배터리 부분에서 화재가 시작됐다는 감정 결과를 내놨습니다.
So as you can see in that particular video that this building, this energy storage system was a complete loss. Once you achieve thermal runaway and propagation has occurred, there really is no way to stop the event from occurring, and you're really just left with letting the building burn itself out. In this particular video, you know, we use lithium-ion batteries in all of our devices now, almost on a daily basis, from cell phones to laptops, cars, and so forth. This particular video, I didn't want to use it to scare you or detour you from using lithium-ion batteries, but I did want it to demonstrate the level of risk that a single battery has during a thermal runaway event and the amount of energy it creates through thermal runaway. So I'll play this video real quick. So you can see even from overcharging just a single cell, there's a significant amount of risk associated with lithium-ion batteries. I think we've all seen this with hoverboards and electric scooters and e-cigarettes, how powerful a single battery failure can be. This is the last video. This video is available online. You can go online and see many different types of off-gas monitoring systems that are available and thermal runaway events that are available. But I wanted to play this video because it has a good timer up here that shows that critical time, that golden time that we talked about, of when off-gas is first detected and the difference associated between the off-gas event being detected and thermal runaway being achieved. So we'll want to pay attention to the bottom of this rack here, and when the clock starts is when off-gas is first detected. So now the off-gas monitor is detected an off-gas event, and the timer is started, and this is now we're in the golden time for early warning detection. So at this time, hopefully we're working in conjunction with the battery management system to eliminate the overcharging or now you can see full thermal runaway was achieved at 11 minutes and 37 seconds after off-gas was detected. So that golden time here was 11 minutes and 37 seconds. So if you look at some of the design considerations associated with energy storage systems, of course, the industry is moving at a rapid pace. Utilities and municipalities are moving away from fossil fuels, states are moving away from fossil fuels, and they're tapping into natural resources. So these types of applications require a tremendous amount of storage of the power to be used for a later date and time, using, like you see there in the picture, some type of containerized unit for storage. This allows the companies to switch from fossil fuels to renewable energies and back and forth at any time. So eventually, as they build up the system, the storage systems enough to where they can switch from one zone to another. So say from zone A to zone B, from zone B to C, and then from zone D back to zone A. And this cycle allows the utilities to be completely independent of fossil fuels. So as we address the risk associated with, say, like containerized units, we look in large part to what we know from early warning detection. And if you consider this to, in the industry, what we've had experience with, this is very similar to data centers, where you have a rack configuration that uses a hot aisle, cold aisle with an HVAC system for cooling, and the ventilation schedule or scheme allows for the cool air to go through the back of the rack, and then the hot aisle, of course, is the front of the rack, being shared between the two racks. So if we were looking to design a system for off-gas monitoring in this type of system, we would want to place a sensor in each individual rack and be able to identify the off-gas event as it occurs inside of the rack. Now, of course, if this is a hot aisle configuration and the racks are sharing the hot aisle, we could look for economies of scale and introduce a methodology where we place one sensor between two racks However, in that type of configuration, you would be introducing dilution factors, and you would be less likely to respond to the event in early enough time, or you may not be able to respond to the event at all prior to thermal runaway. So for this particular example, we have 30 monitoring sensors, 6 reference sensors that you see here as reference detection, and also 3 controllers reporting to the BMS system and the FACU. Where do we place these sensors? Again, going back to what we know from high airflow environments, mission critical type facilities doing smoke detection, we want to place the sensors in the path of airflow. So if you're cooling from the back to the front, you want to place the sensor in the front and in the top of the unit. If you're cooling from the top to the bottom, you place the sensor in the bottom of the unit facing up, I'm sorry, facing sideways to eliminate or reduce the potential for contamination to the sensor. If you're cooling from the front to the back, you want to place the sensor in the back of the unit at the top of the unit. And then of course, if you're cooling from the bottom to the top, you want to place the sensor at the top of the unit facing down in the path of airflow. So as we look for areas of improvements, we look towards the codes and standards. NFPA 855 is now requiring LEL detectors. However, the LEL detectors are not there to prevent thermal runaway. However, to identify possible methane or explosive type environment for first responders. We need city ordinances and mandates for off-gas monitoring in all energy storage systems, power generation facilities, and data centers. Modifying the codes and standards once every 2 or 3 years is not just addressing the issue quick enough. We need to be able to adopt technology and work to identify the risk from a performance-based standard, not just a prescriptive-based standard. So in review, some of the takeaways from today's presentation, of course, lithium-ion batteries do have limitations. They're relatively fragile. They need to be protected. They need to have temperature monitoring. And we need to understand the 4 stages at which battery failure occurs. Stage 1 is the abuse factor. Stage 2 is the off-gas. And that's the critical time, where the golden time, where we need off-gas monitoring and early warning detection. And then, of course, stage 3 and stage 4, where smoke and fire is occurring. Off-gas monitoring can prevent thermal runaway by working in conjunction with a battery management system and eliminating or removing the overcharging and overheating abuse factors from thermal and electrical abuse. And lastly, mechanical abuse cannot be prevented. So thermal runaway is imminent and unavoidable and cannot be prevented. That does conclude today's presentation on energy storage systems, advanced detection methodologies and strategies for energy storage and power generation. Again, my name is Ryan Sandler with ADT Commercial, a member of the National Fire and Life Safety Team. If you have any additional questions, feel free to reach out to me. With that, today, thank you for attending.
Ryan, thank you so much. Great presentation. A lot of great information there, a lot of technical information. I know a lot of us are following along and trying to take as many notes as possible. It's a very popular topic, and we continue to try to learn new things as we move forward with this topic. So thank you. We do have a couple questions that have come in. You do realize that it's a little after 1 o'clock, so for any of you that have to log off, I just want to thank everybody for joining us today. If you have some time to stick around for a couple questions, that would be great. So Ryan, let me start with one of the questions that came in. The question was, is there a significant detectable temperature rise before thermal runaway?
That's a good question. It depends on what the abuse factor is. Of course, from an overheating or thermal abuse factor, a battery management system can identify a rise in temperature and shut down the abuse factor. However, if you're looking for some type of external temperature sensors or things of that nature, I don't think that there's technology on the market today that would be able to identify the thermal event prior to thermal runaway. But a battery management system would be a good choice in identifying that type of an event.
Great, thank you. The next question is, hold on a second, couple more coming in. Which insurance companies, if you do know, are there? What insurance companies are asking for off-gas monitoring?
There's several of them out there that we're seeing that are starting to mandate or look for these types of requirements. And everyone from AXA XL to Chubb, FM, Marsh are all quickly understanding the risks associated with energy storage, and they're looking at how they can and provide some level of preventable measures. FM Global is probably the leader out there that's now requiring off-gas monitoring.
Excellent. And I think it's just important to let all of our listeners know that that's something that you certainly want to ask that question if you're involved in these projects. Find out who the insurance company is and find out what their specific requirements are. Next question came in about unmanned sites. Do you think that it would work in unmanned sites, or is the golden time period too short to have somebody dispatched to site and begin disconnecting?
So I think this is a great topic of discussion with, it's almost a political topic, if you will, given today's political environment. But, unmanned sites largely don't pose a significant amount of risk. However, what we're seeing in states like California or remote sites of where some of these applications are being used is the facility itself is causing a risk to the forestry and causing fires outside of it. So in my personal opinion, I do think that there is value in early warning detection, even in unmanned facilities. But off-gas is not required in these types of facilities currently.
Gotcha. Okay. What about the maximum airflow rating for the sensors? Is there a maximum airflow rating for
those? Typically, the sensors, depending on the manufacturer, do have an operating range, and really you want to look towards some of the technology that we know today, like air sampling, smoke detection. Even though that there is a large amount of airflow in the environment, you're not going to see anything like above, say, 4,000 CFM or something like that. Nothing, terribly crazy, where you're not going to be able to detect the off-gas event from occurring. So most of the sensors on the market today can operate, in a couple hundred air changes per hour, so to speak, in those types of environments.
Great. There was a question that came in regarding asking questions about certain suppression systems and so forth, but this topic really, I know that's part of the discussion as a whole, but we're really focusing on the detection side today, so I'm going to pass up on that question. And then the last question that we have that has come in, you might want to get your lawyer to answer this question, so I'll read it as it's written, and you can answer it accordingly. Can you, with 100% certainty, that this detector will prevent thermal runaway for a quickly developing thermal runaway event?
So I'll take a swing at this one. Off-gas monitoring is not used to prevent thermal runaway. Off-gas monitoring is used to detect an off-gas event that can work in conjunction with, say, BMS type systems that can shut down an abuse factor or eliminate an abuse factor. So much like with smoke detection is not going to prevent the fire from occurring. Neither will the off-gas monitor prevent thermal runaway from occurring. But when you pair off-gas monitoring, early warning detection with the likes of, say, battery management systems, then of course we can address the issue and prevent thermal runaway from occurring.
Excellent. Thank you. And one last thing, not a question, but more of a comment. There was a statement from an attendee who does work for FM, and that individual stated that they do not recommend the Lion Tamer product device, but they did want everybody to know that FM Global is investigating several early detection strategies as well as passive protection options. And it just goes back to what we talked about earlier. Anybody that's involved in a project like this, it's just important to reach out to the specific insurance agency for that project and find out what their requirements are. And I know it also depends on the specific area and so forth as well. So that could certainly change from location to location. So but that's it. We really appreciate it, Ryan. Again, great topic, great discussion, some really good information. Again, I want to thank all the attendees that have come on today and been with us here today and listen to Ryan's presentation. This presentation has been recorded and will be available on our website in the next couple of days. So keep an eye out for that if you want to re-listen to the website, to the webinar, excuse me. And with that, again, thank you, Ryan. Thanks to everybody listening, and I'm going to hand it back over to Becca.
Well, Todd, you said everything I was going to say, so thank you to Ryan and everyone for attending the webinar. And like Todd said, the webinar will be available on the FSSA website for you to re-listen to, and we look forward to having you join us soon.
Thank you very much, everybody.